So we're going to do part two of the Hooke's Law lab. In this particular part of the lab, we are going to look at the period of a spring mass system. In part one, you calculated the spring constant by knowing the force that was stretching a spring a certain distance. And we graphed the force on the y-axis and the mass on the x-axis. And then when we did that, we found that the slope of the line was the spring constant. You have learned previously that the period of a spring mass system is equal to 2 pi the square root of the mass divided by the spring constant. We want to solve that equation for the spring constant and get a value that allows us to, again, graph the system and find that the slope of the line is the same value you measured in part one of the lab. So to do this, we'll take a known mass, we'll take the same spring that you used in part one, and we'll oscillate it, finding the period and knowing that mass, and we'll calculate that out to the equation that you will see on the screen in a moment. So here I have the spring mass system. You can see that I have a mass hanging on here, and I'm going to pull this down and let it oscillate. As I mentioned to you, if you look at the screen, you will see the equation T equals 2 pi the square root of m over k. That is our basic spring equation. And you can see how we can manipulate this so that mass would be on the y-axis and the spring constant would be our slope. So this is mass, this is slope, and 1 over omega squared. Omega squared is equal to 2 pi over the distance, so over the time. So when we are solving this, and we'll talk about omega more at a later point, you will see this is omega, the omega value right here in the equation. We'll talk about that more at a later point. But for today, knowing that we're solving this, m is going to be, again, on our y-axis, and the value that we'll calculate out for omega will go on our x-axis. The slope will be the spring constant. So to do this, I've already put in here our masses, the same masses we previously had. I am going to have a constant amplitude. Amplitude does not affect, we know this, we've heard this multiple times, that amplitude does not affect the period of a spring, but we're going to hold that as a controlled constant variable throughout this lab. We're controlling the distance, so that way it will not have an impact at all, even if it was something that impacted it. So this settles down to just about 32. I'm going to pull this down to 30, and I'm going to release it, and it's going to oscillate. When it gets to the top, at one of the oscillations, I'm going to start the clock. Every time it gets to the top, I will count. When I have 10 counts, I'll record the time. So here we go. I've pulled it down. I'll let it go. It's going to oscillate up and down. I'm going to start our clock. I want to start it right when it's at the top. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I'm going to do that again. 13 I got, 13.03. We'll start it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 12.48. Let's do it one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 12.78. So I'm going to average these numbers together and come up with a value and put it in the table here. Ends up that, and I'm not going to actually use the first one. I've done this experiment before. 12.56 ends up to be right around the average of the trials when we do multiple trials. And then you will take that value and divide by 10 to get the period. The reason that we want to get the period is we want the time for one oscillation. Now I should note that we did 10 oscillations. 10 oscillations is done because there's 2/10 of a second of error in your finger, and that means that there's 2/10 at the beginning and 2/10 at the end. So if we were trying to do one trial, and the period of this is about 1.3 seconds, you're dragging in there about 25% error in your finger. By doing 10 trials, the trial at the beginning has error, the trial at the end has error, but there's 8 perfect trials in the middle, so your error is dropped down drastically. And so you, instead of having a quarter of a 25% error, you're down to about 2.5% error or less in this activity. From there, after you've done the period, you'll calculate the frequency, which would be 2 pi. The radians would be 2 pi, which you could put into the computer. You should be using the spreadsheet program, so you would type in there something like equals 2 times capital P, capital I, capital P, capital I, open close parentheses, divided by, and then you would click on the cell before it. You click over here on the cell before it, which A, B, C, D, E. So we'll say something like E3, something like that. But when you click on it, it'll do it. You then will square that value. So you would square whatever that would be. So if this was EFG, so equal F3 squared. Again, you would click on the previous cell. Type in like that. And then you inverse it. And so it would be like 1 over G3. And that is 1 over omega. That would be your 1. Make sure I put the equal sign there. That would be your 1 over omega squared value. That goes on your x-axis, and the masses will go on your y-axis. You'll graph this out. I am not going to require that you watch all of these trials. I will share with you the data for those trials as well. And the data looks something like this: 8.93, 5.57, and 10.54 seconds. So that you could use those numbers. I'll share that with you as well, but those are the numbers to use. We'll repeat this doing the same process that we did on the main video. We will repeat this using our other spring, the same spring we used in the part 1 of the lab, and you will get the data that you see on the screen as well for that. So again, you can see the data for Hooke's Law device 2, which was spring number 5 of the packet of springs. So we had our packet of springs, and spring number 5 was the spring that we used. You can see the period. And then again, we go back to the first spring. You just watched me do trial 1, but we would repeat that for all of the other trials as well, saving you time. I've put the data in here. If you have any questions, please let me know. You will be working on finding the equation of the line and the slope. The spring constant you calculate should be close to the spring constant you calculated in part 1.